So we're in section 1310. This is our last section of the chapter. And we're going to work on a new method for optimization when we have constraints. So on Friday we worked on a problem. We did a problem where we had we wanted to maximize x, y squared, z such that x plus y plus z was 32. Now in this type of problem, we're going to, what we did on Friday, all of the problems that involved some kind of condition like this, we solved this equation for z usually to eliminate that variable when we took our partial derivative. So we ended up with all of our expressions just in terms of x and y. So we used this equation to make a substitution. We're going to learn a different method to do this kind of problem. What we're looking for in general is we want to maximize, or we want to optimize for this method. We want to optimize some function of x, y, and z. And we call this our objective function. And we have the condition which we usually call the constraint or the side condition. So our side condition is that some function g of x, y, z equals some constant. So in this problem, the problem we did on Friday, our objective function is x, y squared, z. And our constraint was x plus y plus z equals 32. So this is Lagrange multipliers is a method to solve this type of problem where we have an objective function and we have one or more constraints that we're working with for our objective function. So let's draw a picture to give a kind of a suggestion as to why the method works. So we have an objective function and we have our constraint or our side condition. Now g of x, y, z equals k. We're going to think of that as first we're going to look at a two-variable function. So we're going to look at our objective function as being f of x, y, and our constraint as g of x, y equals k. So for a two-variable example, our objective function is f of x, y. We want to optimize that. And our constraint is g of x, y equals k. Now we can think of g of x, y equals k as one level curve of the function g of x, y. And we're going to graph this level curve of g of x, y, and we're going to graph several level curves of f of x, y. So we're going to graph some level curves of f, and we're going to graph and the one level curve of g of xy equals k. we're going to put those on the same graph. And this is going to give us our kind of it's a little bit of a hand-waving argument, but why the method's going to work. So here are our coordinates in the XY plane, our axes. And let's say that this red curve, this is g of xy equals k. So that's our level curve of g. And we're going to graph several level curves of f of xy. So here is one. I'll do that in a different color. And we're going to say that these purple curves are functions of f of xy equals some constant. And we're going to say that this curve is our constant equals 1, constant equals 2, constant equals 3, constant equals 4, and constant equals 5. So looking at these curves, we're maximizing the purple, the f of xy, the purple function, subject to the constraint g of xy equals k. Well, where on my sketch is f of xy maximum on this red curve? When this constant equals, when f of xy equals what? When it's 3. It could be a min or a max, depending on whether the surface is going uphill or downhill, right? So it's optimized at constant equals 3. Well, what do we see is happening there? It's tangent at that point. So everywhere else, it's either not on the constraint, or it's not a maximum or a minimum. It's not an optimum value. So when we obtain a maximum value of f, our function and our constraint share a tangent line. So that's going to be the important thing for our method. So the maximum occurs, or the optimum value occurs, where they share a tangent. Now, in terms of quantities that we've been working with in this chapter, if their tangent lines are parallel, they share a tangent line, what quantity that we've been working with in this chapter is also going to be parallel? The gradient, because the gradient is orthogonal to the level curves. So the gradient is orthogonal to the tangent line. So our gradients are going to be parallel, and that's what we're going to work with. Because they share a tangent line, the gradients are going to be parallel. So del f and del g are also parallel at that point. And since the gradients are parallel, we can write at that point that del f at the point that we're interested in, x0, y0, equals lambda del g at that point, x0, y0, for some scalar lambda. And lambda is our Lagrange multiplier. So based on our kind of little bit of a hand-waving argument, we're not making it rigorous, but we've suggested why it works. We've come up with the method that we're going to work with Lagrange multipliers. Now before I write the theorem and before we do an example, I wanted to mention also that this Lagrange multipliers is related to linear programming. I don't know if you remember doing linear programming in probably Algebra 2, where you have, you probably did it when you solve systems of equations, and you had some region in the xy plane, and you were trying to optimize your function, and you had to solve simultaneous equations to find the corners of your region, and you figured out that the optimum values were going to be at the corners. That's related to what we just talked about, because our optimum values where the two functions, the objective function and the constraint, are tangent. So we're looking for, in linear programming, that's going to happen at the corners of the region where the objective function and the constraint intersect at a single point. Linear programming works a little more nicely because our constraints are linear functions, and here our constraints are multivariable functions. All right, so now we can go to Lagrange's theorem. We have an idea of why this works, so we'll state the theorem that we're going to work. And then we're going to do an example. So Lagrange's theorem tells us that if f and g have continuous first partials, and f has an extreme value at some point x0, y0 on the smooth constraint g of xy equals k, then del f at x0, y0 equals del g, equals lambda del g at x0, y0. And we're assuming that the gradient of g at x0, y0 is not 0. If del g is 0, then we have to figure out some other method to use. We call lambda is the Lagrange multiplier. And we're also saying that lambda is a scalar. So that's our theorem. When we apply this, to apply Lagrange multipliers, questions before we go on? Okay. So the method to apply. We're finding the extreme value of some f of x, y, z with the constraint g of xyz is some constant. We're going to find our x, y, and z and lambda such that del f equals lambda del g. And we know that g of xyz equals c. So we end up with a system of equations from this condition. We end up equating components. We evaluate f at all of our x, y, z from using Lagrange multipliers. The largest is the maximum, and the smallest is the minimum of f subject to that constraint. So we just apply this method, find our x, y's, and z's that make this true, and the largest value is going to be our maximum on that constraint, and the smallest value is going to be our minimum on the constraint. And we can use Lagrange multipliers if we have more than one constraint. If we have multiple constraints, if we have two constraints, and our two constraints are g of xy and h of xy. Each of these are some constant. Those are two constraints. We use two Lagrange multipliers. And we write that del f equals lambda del g plus mu del h. And for this condition, we have to have del g not parallel to del h. So if we have more than one constraint, we just add another term to our equation for Lagrange multipliers. We end up with two Lagrange multipliers. Now the benefit of using Lagrange multipliers over the method that we've used in the past, where we've set our first partials equal to 0, find where each one is simultaneously 0, and use substitution like we did on our last homework assignment. Lagrange multiplier can be a little quicker and easier to apply, and it will also, we can often use Lagrange multipliers when our function is complicated and solving simultaneous equations and substitution is very difficult or even not possible. So it just gives us another tool to use for optimization. Questions before we do an example? All right. So let's look at an example. So we have f of xy equals e to the minus xy over 4. And we want to optimize, we're optimizing this. And our constraint is x squared plus y squared is less than or equal to 1. Now, because we have a less than or equal sign here, we have two conditions. We have x squared plus y squared equals 1, and that's the condition we're going to use Lagrange multipliers on. And we have x squared plus y squared is less than 1 on the interior of our region, and we're going to use methods on the interior of the region. We're going to use methods that we've already talked about. So for this one, we're going to use Lagrange multipliers. And this, we're going to use partial derivatives. So let's look at the boundary first. On the boundary is where we're going to use Lagrange multipliers. So this is our objective function, and this function is our constraint. X squared plus y squared equals 1. So that's our constraint. So del f, I'm going to go through relatively quickly so we can get through this example. Del f is minus y over 4 e to the minus xy over 4I minus x over 4 e to the minus xy over 4j. And del g our constraint, x squared plus y squared equals 1. Del g is 2xi plus 2yj. And we're going to say that del f equals lambda del g, and we're going to equate components. So when we're going to equate our components. So minus y over 4 e to the minus xy over 4 equals lambda 2 lambda x, and minus x over 4 e to the minus xy over 4 equals 2 lambda y. And I'm going to solve each of these for lambda. I'm going to solve each of these for 2 lambda. So 2 lambda equals minus y over minus y over 4x e to the minus xy over 4, and that also equals minus x over 4y e to the minus xy over 4. What's that?
Can you switch the fraction? Oh, you solved the other one.
Right, I solved each of these for 2 lambda, and then I just set them equal to each other. And this equation, minus y over 4x e to the minus xy over 4 equals minus x over 4y e to the xy over 4. If I solve that, that gives me x squared equals y squared. And on my constraint, On my constraint, x squared plus y squared equals 1. So we're on our constraint. So x squared plus y squared equals 1. So 2x squared equals 1. So x equals plus or minus square root of 2 over 2. And y squared, I can plug this in back in here to solve for y squared. And y squared is, y is plus or minus square root of 2 over 2 also. And our points are, we have, because we have plus or minus and plus or minus, we end up with two sets of points. We have, when they're the same sign, we have plus or minus square root of 2 over 2 and minus plus square root of 2 over 2. And we have, when we have the same sign, plus or minus square root of 2 over 2 and plus or minus square root of 2 over 2. These have opposite signs. If we run this through, we find that that we have all four of these possibilities. We have when x and y are opposite signs and when x and y are both the same signs. And when we plug this x and y back into my function, into our objective function, this one here, I get that f equals e to the 1/8, which is approximately 1.1331. And here we get f equals e to the minus 1/8, which is approximately 0.8825. So on the constraints, these are our maximum and minimum values, e to the 1/8 and e to the minus 1/8. We still have a little bit of work to do, though. Yes?
Where did you get the x squared equals y squared?
When I solve this equation, e to the minus xy over 4 is on both sides, so they cancel. Then I just cross multiply. The minus signs cancel and 4's cancel, and I get x squared equals y squared. Okay? So these are the values on our constraint. We still have the interior to look at, because that's our second condition, where x squared plus y squared is less than 1. For that, we're going to use the methods that we've used previously. Our Lagrange multipliers we only apply on the boundary, so we're going to use our previous methods on the interior. So let's look at the interior now. Where x squared plus y squared is less than 1. We're going to find our first partials. The first partial with respect to x, we already figured out, minus y over 4, e to the minus xy over 4. F sub y is minus x over 4, e to the minus xy over 4. And we want both of those equal to 0. We're looking for our critical points. And the only time when both of these are 0 is x equals y equals 0. And on our interior, we have a number of possibilities for this point. It could be a maximum, it could be a minimum, it could be a saddle point. So we need to run our second partials test on the point 0, 0. So we find our second partials, f sub x is y squared over 16. No, because we end up with another negative there. F sub y is x squared over 16, e to the minus xy over 4. And our mixed partial, f sub xy, minus 1/4, sorry. And at 0, 0, our second partials test, f sub x, xx, f sub xy, minus, I'm sorry, yy, is less than 0. So 0, 0 is a saddle point. So our minimum is e to the 1/8 at plus or minus square root of 2 over 2 minus plus square root of 2 over 2. And our max, sorry, this is e to the minus 1/8, and our max is e to the 1/8 at plus or minus square root of 2 over 2 plus or minus square root of 2 over 2. So like our other problems, this takes a fair amount of work. But examining our maximum minimum on the boundary with Lagrange multipliers, not that difficult. Set up our equation and we equate components, and we can find our maximum minimum relatively easily on our boundary. And just really quickly, I made a graph of this surface to show our maximums and minimums. So let me get to that. Let's see, do you see it? 13. There we go. So there's our surface. And our saddle point here at 0, 0. And our maximum here, and the circle is our constraint, x squared plus y squared equals 1. So on the boundary, our maximums are here and here, and our minimums are here and down over here. So a graph of our surface with our constraints, and we can see what we came up with there. Any questions? Now tomorrow we'll review. I'll give you some review problems, but I do want to do one more Lagrange multiplier example with 2 constraints. So we'll look at our Lagrange multiplier problem with 2 constraints. We won't have to look at the interior. We'll just have to look at the constraint, so it'll go a little more quickly. So our homework. There you go.